alright, so I was just talking about this, but the poles of the Laplace transform are the points at which infinite oscillation occurs, also known as balance states or stable orbits. These are points where the mass cancels and they are, relatively speaking, the same mass. In order for the planets to survive this long, they need to establish themselves into stable orbits on these poles. As you move out, though, there are more constants that add noise to the system and shift the pole's location. Negative mass or no mass is infinite energy. This can be seen on the plot, right? This is why we can get so much energy from dark energy, potentially. I don't know. And then I just have some images here. So basically what I'm saying with this is that, like, honestly, like, I don't even know if, like, like, I still don't have a perfect concept of understanding for this, but I do just want to kind of put it out there because I think it's an important thing to tie in with my understanding of orbital motion. And I feel like because of the way gravity works, and we observe this on the planetary scale, on the celestial scale, with stars, with black holes, with galaxies, everything spins. Everything spins. Everything moves around, like when objects get to a certain, like, frame of mass, right? When things have enough mass, right, relative to each other, if they both have energy as they approach, right, they will move towards each other, right? And then kind of, like, if they kind of miss each other, right, as long as they don't have a direct line with each other, if they have a direct straight-on path, boom, they'll collide, right? But if they're just slightly off, like if one is moving this way while this one's coming this way, right, they'll miss each other. But then they'll be interlocked they'll get caught in each other's gravity, right? And so they'll get interlocked and they'll go, oh no, and then eventually, over long periods of time, depending on how much energy is there, they finally collide, right? And so the majority of collisions, which can also be considered as interactions, the majority of interactions do not play out as direct collisions. Rather, it is this oscillating rotational motion that we end up observing instead. That when you look at it from a certain perspective, it can be extrapolated to this linear motion that appears as waves. This is why we think everything is waves, because everything is rotational motion, which when you look at it from a certain perspective appears as waves. Right? And so it looks like, wow, it's going farther away and getting closer, farther away and getting closer, farther away and getting closer. Just like up and down on a wave. And it's not a wave, it's rotational motion. And I think this is important because we observe the emergent behavior of rotational motion and not the individual behavior. Right? And so we are looking at the emergent behavior and assigning it as the original. And I think that this is a flaw, and this is why we're getting so caught up on this. And the reason why all of our equations and everything works with waves is because what we're actually doing is we're doing a rough approximation. We're taking, this is rotational motion, and we're converting this rotational motion, boom, into a waveform. And then we are using that waveform to actually perceive as reality and use for our calculations and our equations and stuff. And we have tools for this. We have I don't know if one goes the other way, one goes the other, kind of blanking on it right now, but the Laplace and the Fourier transform both play with this. Kind of going from one to the other, right? And we have the tools to convert it. We can now comprehend, okay, like I don't know if those things were a thing yet. When these theories were first being developed for wave theory and stuff, I don't know if those were a thing yet or not. But if they were, maybe we should have considered that. But I'm not so certain that they were. Maybe they were, I don't know. And so we now have the tools, though, to deconstruct these waves that we are observing, right, into what the reality actually is, right? Because no one looks at the ocean and goes, those waves are the base of water. Water is actually just a wave, right? No one looks at water and thinks, that looks like a wave, right? Because when you look at a glass of water that's still, you do not look at that and go, really wavy. No, because it's not waving. Because it's not a wave. It aggravates me a little bit. I'm sorry, right? Because it doesn't make any sense, right? We look at the ocean and we go, a perfect example of waves, right? But then we look at a pond and go, no waves here. Let's ignore that, right? It doesn't make sense. What does make sense is this rotational interaction is what happens here. And when a collision happens straight on, it's not that this rotational thing is thrown out the window. It's just that the equation, like technically there is a rotational thing happening here, right? But they just, the trajectories just are too close that the orbital is just straight on, right? And you can do the math and you can find this. And I think I've seen videos talking about this and I was like, yes! But I don't think that it's really taken to its full extent. And I think the full extent is that everything is this orbital interaction and stuff. And you look at everything and it's spinning. You look at molecules, you look at atoms, everything is, we say that at a certain size, we're like, electrons have spin, but they're not actually spinning, right? And so we have all these things and we refer to it as spin because it appears as it's spinning, but we say it can't possibly be spinning. That's a whole other thing. I think that potentially, yes, it is spinning. It's just, it's not observable to us. And that gets into another talk that I just did about how some things just really aren't observable to us, even though they are in fact real. But that's besides the point for this talk. And so, everything we can look at it and we go, wow, it's kind of like spinning. It's kind of oscillating. It's got like this motion here. And oscillation is just like if you graph oscillation, it turns into rotation. It's just what it does. Like if you draw like the dampening of like a spring, right, or something, right? It looks like this when you draw it out that way, but if you put it on like if you convert it, then it's just a spiral inwards until it stops. And I think that is so important because we see this spiral behavior all over the place. We see it everywhere. And the reason why we see it everywhere is because it is the backbone of reality. This is why pi shows up everywhere. Because circles and rotation is everywhere. This is why the golden ratio in phi, and we see that and we observe it everywhere and everything seems to follow this because that is what nature is. It's rotational behavior. It's just how it all happens. It's just what what it does, right? And so I think that this is very easy to see and the evidence is there and it's so easy to observe in the world, right? But we don't. Right? Like we go, oh yes. But I feel like it's not taken till its true significance to be truly realized as for what it is. And I think the key to understanding this in potentially understanding certain aspects further is to utilize these transforms and, convert it into something that we can comprehend. We're like, what's going on here? I don't know. Convert it into something that makes more sense, right? And I think we can do that. And I think that there is, I don't know what these transforms are currently being used for, right? But I think they could be used for more, potentially. Maybe I'm way late to the boat on this, and this is old news. And if it is, then good. But if this is old news, then what the heck are we doing? Because it should be obvious by now, right, that waves are actually just rotational motion, and that rotational motion is is actually what is creating is what's creating this, right? This wave behavior, this wave motion that we see everywhere, and is what has kind of clouded our judgment into everything is waves. It's like we're just totally tripping out on our own BS right now, and I hate it. I don't like it. And we got to take a step back and realize, there's another level here, and like I said, I don't know what is and isn't understood about this and the capabilities of it and what it's been done with, right? But a part of me just feels like, me saying this is important, and it's not actually common knowledge, and it's not actually being utilized in the proper ways necessarily. Not that it's being used wrong, but it's not being used enough, I think is maybe a better way to say it. It's not being used in all the ways it can be used, because if it was, I feel like it would have been clear to us. Like, I wouldn't need to be saying this right now. I wouldn't need to be saying this, and I wouldn't need to be making any of these videos probably. But I do, and I am, because it's not, I didn't find anyone talking about this, right? We observe it, we know that it's there, but I didn't see anyone talking about it. And I'm going to go into spectroscopy in my next video, but it is basically taking this rotational motion, right? And you're like, oh wow, it's spinning at a certain speed. Because it's spinning at a certain speed, like we know this. You can use spectroscopy to figure out the energy, like the rotational energy. At least I'm pretty sure this is how it works, right? Or maybe I'm misunderstanding the spectroscopy, right? But I'm pretty sure this is how it works. You can use the spectroscopy of an atom to figure, or like of a molecule, to figure out its energy and like its like rotational speed and all these different interactions. Like, you can use the spectroscopy to figure this out, right? And the fact that you can do that, I feel like, is just such an obvious, hey, this is rotational motion creating wavelengths. Maybe there's something here. Like, maybe we should think about this a little bit. Like, I don't know. I'm gonna talk about it some more in another video. Peace out.